Alright, welcome back again to our video lecture in ENSC107. Now in this video we'll be doing a sample problem for the multiple pipe systems in a parallel connection. Alright, the problem says that we have two pipes that are laid in parallel as shown in the figure. Here's our figure. So we have a branching pipe. Let's say this is our pipe 1 and we have another branching pipe, and this is our pipe 2. It says here that the pipe characteristics and dimensions are as shown. So the length for pipe 1 is 100 meters, and our relative roughness, it's already given 0.013, and the diameter here we have 20 cm. Now for pipe number 2 we have the same length, L is equal to 100. The diameter is 30 cm. So this is larger as compared to pipe number 1. And the relative roughness is 0.0015. Okay, if the total discharge is 0.35 cubic meter per second and the water temperature is 25 degrees C, what will be the discharge in each line? Assume initial F value of 0.02. Okay, so the total discharge is 0.35, but the but the problem asks us to find the discharge in each pipe, and we know that for a parallel connection we know that the Q total is equal to the flow rate in this pipe 1 plus the flow rate in this pipe 2. So since in this, with respect to pipe 1 and pipe 2, we don't have the flow rate, and therefore this is not a type 1 problem. And that is why it says here that we will assume an initial F value of 0.02. So it's an iterative solutions. Okay, so for the solution, so first step is recall, right? Recall that in parallel connection we have this relations. Q total is just simply the Q1 plus Q sub 2, and our head loss, our total head loss, is simply equal to H sub 1, and this is also equal to H sub 2, and our head loss at 1 is just simply a function of we can use the Darcy-Weisbach equation to solve for the head loss at point 1, and that's just simply equal to the head loss at point 2. Let's say this is our equation 1 and this is our equation number 2. Okay, so the next step is since headless at pipe 1 is equal to headless at point 2, then we can apply the Darcy-Weisbach equation. Okay, this must be capital Darcy-Weisbach equation. Okay, so FL over D, so that's at point 1, or H sub 1 is simply equal to H sub 2. So FL1 over D times the velocity head V squared all over 2G is equal to FL over D at pipe number 2 times the velocity head all over 2G. Okay, so we have the value of F, because it says here we'll assume an initial value of 0.02. Okay, so F, our L is also given, and our D is also given, and this one 2G is equal to 2G. That's just the same, so we can cancel this out. And our length, since they're the same, The given is 100 for L1 and also 100 for L sub 2. And therefore, we can just cancel this. So what's left is um, also, I guess the friction factor, they're just the same, so we can cancel this. So what's left is v squared all over d1 is equal to the velocity at pipe 2 divided by the diameter at 2. Okay, so we can actually, in this step, we can obtain a relationship between the velocity 1 and the velocity 2. So substituting now the values we have, v sub 1 squared all over our d sub 1, which is 20 cm, so that's 0.2 meters, okay, is equal to the velocity at 2 squared times 0. Okay, this one is 30 cm, so 0.3 meters. Therefore, we can obtain v1 is equal to 0.363 is the velocity at 2. Okay, let's say this is our equation number 3. Oh, sorry. This will be v squared, and we'll just I guess I have to check this. This is 1 divided by 0.2, right, divided by, or let's say 0.2 divided by 0.3. So 0.667. Right, so this one is wrong. So this is 0.667. Now, if we take the the square root, this is v sub 1 is equal to 0.816 v sub 2. Okay, so this will be, I think, this will be our equation number 3. Okay, so from v squared, so if we take the square root of both sides, then this v sub 1 squared will just will reduce to v sub 1, and this one will be 0.816, and this square of this v sub 2 will just reduce to v sub 2. Okay, this is our equation number 3. Okay, so the next step is to substitute equation 2 to equation 1. Okay, so this is our equation 1, and we know that the Q total is equal to the velocity at 1, right, times the area at 1, plus the velocity at 2 times the area at 2. Okay, so we have to express this v sub 1 in terms of v sub 2. Therefore, this is 0.816 v sub 2 times the area at 1, which is just pi d squared, 0.2 squared all over 4, right, plus this term, which is simply v sub 2 times pi d squared, but this one, the diameter is 0.3 squared all over 4. Okay, so here we get v sub 2 is pi, sorry, this is no longer pi. I guess this should be, if we do the computation, what we get here is 0.0963. Right, this is our Q total, but the Q total is 0.35. So this is 0.35, and therefore v sub 2 is equal to 3.63 meters per second. Okay, now we have, since we have the velocity 2, and let's say this is our equation number 4, so we can solve now for the v sub 1. So step number 4, Substitute equation 4 to equation number 3. Therefore, v sub 1 is equal to 0.816 times the velocity 3.63 meters per second. 0.816 3.63, that's 2.96 meters per second. And now let's write this is our equation 5. This is our equation 5. So the next step is since we have the initial velocity, then we can solve for the Reynolds number. Okay, so take note again that this problem is not a type 1 problem, meaning that the flow rate is not given, and therefore we have to do iterations. So we have to guess actually the friction factor, and then iterate if necessary. Okay, so this velocity is obtained from an initial friction factor, but we have to check now. We know that the friction factor would be different because we have a relative roughness that's different. So we have a different value. This is 0.013. This one is 0.0015. Plus the velocity is different, and therefore the friction factor would be actually different. Okay, so let's solve for the Reynolds factor. Reynolds factor. I mean the Reynolds number. So once we obtain this, and since we have the relative roughness, then we can find the friction factor from the Moody diagram. Okay, so RE at point 1 is just simply equal to rho LC times velocity divided by the viscosity, or in terms of the kinematic viscosity, this is just simply the characteristic length times the velocity divided by the kinematic viscosity. So here, if we substitute all the value, our velocity is 2.96, and our characteristic length for pipe 1 is since this is a circular pipe, then it's just equal to the diameter, which is 0.2. Right, this 0.2 divided by the this value, which can be obtained from tables. So 0.893 times 10 to the negative 6. Now if you do the computations here, what you'll get is 2.96 times 0.2 divided by 0.893. Right, take note this is times 10 to the negative 6. This is 602,933. Okay, and then for the Reynolds number at pipe number 2, we have the velocity. The velocity is 3.63. So this is 3.63 times the characteristic length, which is just the diameter itself for a circular pipe, okay, divided by this kinematic viscosity, 893 times 10 to the negative 6. Okay, so 3.63 times 0.3 divided by 0.893 raised to negative 6. And this is 120, I think 1,219, right? 804. Okay, so our step number 6, since we have the Reynolds number and the relative roughness, we can go, or we can obtain the friction factor F1 and F2 from the Moody diagram. Okay, so our F sub 1 is equal to 0.021, and our F sub 2 is equal to 0.0145. Okay, so this is now our corrected friction factor. So um, therefore, applying again equation 2. So H sub 1 is equal to H sub 2. So it's just FL times V squared all over 2G, right? Is equal to FL over D times V squared all over 2G. So our friction factor is 0.21. Right. Our length is 100 meters times our velocity at 1. We can't use the value, this value, simply because this value um, is obtained from an assumption that or from an initial value of friction factor of 0.02. So this is what we are going to solve, right? V squared all over 0. Right. So we have 2G. We have the same value of 2G. Actually, the length is also the same, or we'll just write it. Anyway, it doesn't matter. So 0.2 is equal to the friction factor at 0.2, 0.0145 times the length of 100 times the velocity at pipe 2 squared divided by the diameter. Okay, so this one cancels out, and therefore we have 0.021 divided by 0.2. So this is 0.105 v sub 1 squared, and then this one is 0.0145 divided by 0.3. This is 0.048. Right. And therefore, um, and therefore we can solve for the velocity at 1 is equal to 0.46, right? I think this one is squared, then v sub 2 is squared. Okay, therefore v sub 1 is just simply equal to 0.676 v sub 2. Okay, now this is our equation number, I think this is our equation number 6. Okay, now we have, since we have this relation, then we can solve for, or we will apply again, applying equation 1. We'll apply the equation 1, which is q sub 2, q total is just equal to v sub 1 times the area of pipe 1 and plus the velocity at pipe 2 times the area at pipe 2. This 0.35. This one, the velocity is okay, so the velocity is 0.676 v sub 2 times the diameter of 0.2 squared by d squared all over 4, or we can just factor the pi over 4 plus the v sub 2 times the diameter of pipe 2, right? So times pi over 4. Okay, so now let's simplify. We'll simplify this 0.676 okay, times zero point 0.2 squared plus 0.3 squared, okay, times pi divided by 4. Okay, so this is, or let me check again, 0.676 times zero point 0.2 squared, right, plus 0.3 squared times shift by divided by 4. So this is 0.0919 v sub 2 is equal to 0.35. Okay, and if we solve for v sub 2, what we get is 0.35 divided by the answer. That's 3.81 meters per second. Okay, therefore, v sub 1 is equal to 0.676 times 3.81, okay, meters per seconds, right, times 0.676, 2.57. That's 2.57 meters per seconds. Okay, the next step is since we have v sub 1 and v sub 2, therefore we can solve for q. So q sub 1 is just simply the area at pipe 1 times the velocity at pipe 1. So the area is just pi. The pipe 1 is this is 0. I think this is 0.2, right? Pi d squared all over 4 times the velocity at 1, which is 2.57. Okay, and that's 0.2 squared times pi divided by 4 times 2.57. So we have 0.08, let's say 81 meter cube per seconds. And for the flow rate at point 2, we have area at pipe 2 times the velocity at pipe 2. So area is pi d squared all over 4 times the velocity at 2, which is 3.81. That is 0.3 squared times shift pi divided by 4 times 3.81. We have 0.269 cubic meters per second. Okay, now we'll do our recap on our solution. So the problem is we have a parallel pipe systems. So the given is the geometry, but we don't have the flow rate for each pipe. So recall that anytime we don't have the flow rate, then we have to do iterations. Okay, what's given is the flow rate, but this flow rate is the total flow rate. But with respect to the pipe 1 and pipe 2 itself, we don't have the flow rate. So again, we have to do iterations. Now, the first step that we did is was to recall the relationship or the rules in these parallel systems. So for the flow rate, we have an additive flow rate, that's Q1 plus Q2, and that's equal to the total flow rate. But for the head loss, we just have the same head loss. We have equal head loss. Okay, so since H1 is equal to H2, then we can apply the Darcy-Weisbach equation. We apply this because we want to actually solve for something, and what we can get from here is that we can solve for the relationship between the velocity at point 1 and the velocity at point 2. Okay, so we lay down the expression, and we first assume that we have an initial value of 0.02 for both pipes. Okay, so if we assume this one, then in this equation we can actually we can just actually neglect this because they're the same. So the friction factor is the same. The length is also the same because the given is 100 meters, and this one is also 100 meters. The 2g in the denominator is the same, so it also cancels out, and what's left is simply the velocity and then the diameter. So from here we obtain the expression 0.816 v sub 2 is equal to the velocity at 1. But take note that this expression is based on the assumption that we have a friction factor of 0.02. But in reality, we have a different velocity here. I mean, the pipe 2 will have a different velocity than pipe 1. Plus, the given here is we have a surface, relative roughness 0.0015, and this one 0.0013. So they're actually different, and therefore the friction factor would be different. Okay, but anyways, we just assume for now, and we get this expression. Okay, now since we have this expression, then we can solve for the velocity at point 1 and velocity at point 2 by applying the equation number 1, which is the rule number 1 for parallel connections. So it's just the flow rate equation. Okay, now since we obtained the values for the velocity 1 and velocity 2, then we can actually solve, or we can now solve for the Reynolds number at pipe 1 and pipe 2, simply because we now have the velocity. Now we need this Reynolds number because we want to find the corrected value of the friction factor. Okay, so we just apply the equation and we obtain this Reynolds number. And since we're also given with this relative roughness, then we can go to the Moody diagram to obtain the friction factor F1 and F2. Now here the F1 is 0.021, F sub 2 is 0.0145. Okay, so this is now our corrected friction factor, which is different from our initial value. Okay, now by having these values for the friction factor, then we apply again the rule number 2, that the head loss at 1 is just equal to head loss at 2. That's the Darcy-Weisbach equation. And we again solve for the relationship between the velocity at 1 and then the velocity at 2. And we obtain the values of velocity at 1 and 2 by applying again the equation 1, or this rule number 1 for parallel connections. Okay, so once we have the velocity, this area is already given, then we can solve for the flow rate. So that's the flow rate. Flow rate 1 is 0.081, and this one for flow rate at 2 we have 0.269. All right, now in the next video we'll be moving on to our next topic, which is the open channel flows. See you in the next video.